66 million years ago, an extraterrestrial body 6 miles in diameter hit the Earth, making a crater over 100 miles wide and wiping out the dinosaurs. This is the largest extraterrestrial impact known from the past 2 billion years. So where did it come from? How did it come to Earth, and how did it cause so much damage? This story is improbable. In fact, it's one of the most extraordinarily improbable things that's ever happened in the history of Earth. For more than a century, the extinction of the dinosaurs was a complete mystery. No sooner had we discovered these things and figuring out how diverse and strange and wonderful and terrifying they were, we started asking, well, what happened to them? Why did they go extinct if they were successful for so long? For 150 million years, dinosaurs dominated the planet. Then suddenly they all disappear, along with about 90% of all species on the planet. And as the fossil record became better, as we found more fossils, had a better idea of when these fossils appeared, and sampled more parts of the world, this problem only became bigger. The disappearance of the dinosaurs only became more mysterious the more we knew about it. We saw massive numbers of species perishing at the same time around the world, in marine ecosystems, in terrestrial ecosystems, and this seems to have happened almost instantaneously. On land, the ecosystem was devastated to the point where no terrestrial animal larger than a cat appears to have survived. So what could possibly have done this? There were a lot of different theories thrown out, but in 1980, physicist Luis Alvarez came up with an answer. He discovered that there was a thin, globally distributed clay layer that marked the extinction horizon. This is the Cretaceous-Paleogene boundary. And whereas a lot of other geological boundaries are just kind of like they're lines we draw on the stratigraphic column, this is a physical structure, a physical boundary, this claystone that's found all across the world. And it separates the era of the dinosaurs, the Cretaceous, from the era of the mammals, the Paleogene. And when they studied the chemistry of this layer, this odd clay layer, it's not typical for stratigraphic units to extend around the world. It's actually very, very unusual. It's the only case I know of something like this happening. They found this unusual layer was enriched in iridium. Now, iridium is not very common on Earth. It's very dense, so it sinks to the Earth's core, so there's not a lot of it on the surface or in the crust. But it's really common in asteroids. And this was kind of a hint that something really extraordinary had happened here. What they proposed was that there was an extraterrestrial impact by a comet, and it delivered all this iridium to Earth, and that this somehow wiped out the dinosaurs. It knocked up a lot of dust and debris into the atmosphere and caused darkness and cooling. And this idea was initially treated as highly speculative, but soon afterwards, other evidence of an extraterrestrial impact was discovered. One form of evidence that emerged was shocked quartz. And these are quartz crystals that show these microscopic planar structures inside that are deformations caused under extraordinary pressures. And the only place we found shocked quartz occurring on Earth are in meteorite impact craters, things like Meteorite Crater in Arizona, and nuclear bomb test sites. So it gives you some idea of the pressures required to distort the quartz crystals in this way. Quartz crystals are pretty resilient. Another piece of evidence of extraterrestrial impact were these things called spherules. And these are really strange little structures. They're these really tiny, like millimeter scale beads of glass. And they're formed when rock is melted by extreme temperatures and pressures. And then it cooled and hardened, and these beads of glass fell out of the sky. It's basically a hail formed from molten rock shot into the sky by an asteroid impact. And so this provided evidence that the end of the Cretaceous was in fact marked by an extraterrestrial impact, this iridium, the shocked quartz, and the spherules. But what we did not have yet was a crater. If there was an asteroid impact, there must be a crater, and you'd expect it to be a really, really big one to create a debris field that would be found around the entire world. So finally, I believe in 1991, they discovered the smoking gun, or rather the bullet hole. And this was the crater formed by the impact. And it had been eroded for 66 million years and buried deep under the Yucatan Peninsula by sedimentation under marine carbonates, so that it's almost invisible from the surface. I've been out there and there's almost no trace of it. There are these sinkholes called cenotes that kind of run around the edge of the crater, so you can kind of see where the crater is by these sinkholes. And also, you drive over the edge, like you go down about 10 feet and you kind of come back up. There's a little bit of unevenness at the edge of the crater, but it's almost impossible to see this thing from the ground. It's barely visible from space. However, when they did this kind of gravity imaging, the rock has different density and it has slightly different gravitational field than the surrounding rock. And they were able to image this deep buried structure. And it is one of the most extraordinary geological structures on Earth. So it's called the Chicxulub crater because the epicenter, that is the very center of the crater where the asteroid hit, is directly below this little Mexican seaside town called Chicxulub. And the crater is huge. It has a diameter of 110 miles or 180 kilometers. It is one of the largest craters that has ever been identified on Earth. And it is the biggest that we've been able to identify in the past, something like 2 billion years. Further work on the crater has shown that the impacting body punched a hole about 25 to 30 kilometers deep into the Earth's crust, and then crust rocks rebounded upwards to form a central peak and then several rings around that central peak. So it's a multi-ringed crater. This is something we've seen on other planets, but we had not previously seen anything like this on Earth or identified anything quite like this. So the discovery of a crater made the debate real in a way it hadn't been before. This is not a hypothetical. We had this giant crater. And since then, the fossil evidence that's come out has shown that the impact does seem to have been the primary, probably exclusive driver of the end Cretaceous mass extinction. The various things like dinosaurs and fossil mammals and extinct birds and all these things, ammonites, plesiosaurs, mosasaurs, all these things are thriving up until 66 million years ago when this impact happens, and then they all disappear. So it appears the Chicxulub impact is driving the extinction of the dinosaurs and something like 90% or maybe 95% of all species on Earth. This is, again, it's just an extraordinarily large crater. To find anything bigger, you need to go back more than 2 billion years. This is the largest confirmed impact that we have. There are other hypothesized ones that are kind of debated, but this is the largest firm evidence we have for a crater of this size in a 2 billion year interval. So some larger craters have been suggested, like Morakwein crater in the Jurassic of Africa, but the confirmed diameter is about half the diameter, slightly less than half the diameter of Chicxulub. I guess I'm not an impact geologist, but my suspicion would be if it really was as big as Chicxulub, we should see a much bigger debris field than we do, a global debris field. Given that we don't, I would tend to suspect on that basis of that evidence that it probably isn't really that big. So this tells you something about how extraordinary the Chicxulub impact event was. It's something, it's sometimes been called a once in 100 million year event. It might be closer to the truth to say that this is a once in a billion year event, but it was an extraordinarily rare, extremely improbable event. So how did the impact wipe out the dinosaurs? It's not really accurate to call the Chicxulub impact a catastrophe. Rather, it would unleash a series of catastrophes. It's kind of like in the book of Revelations, there's a whole bunch of terrible things that happen at the end of the world. And that's sort of what happened here. This wasn't a single disaster, but a series of disasters, one after the other after the other. It just kept getting worse and worse and worse. So when this thing hits, it releases the energy of, it's traveling so fast, 50,000 miles an hour. That's about 60 times the speed of sound, 25 times the speed of a rifle bullet. So it's creating an extraordinary amount of kinetic energy. Kinetic energy is proportional to the square of velocity. If you remember basic physics, you're traveling at 50,000 miles an hour, and you're a 10 kilometer, 6 mile wide mountain of rock that has an extraordinary amount of kinetic energy. It's equivalent to something like 100 billion megatons of TNT. This is roughly proportional to, around about 10 billion atomic bombs on the scale of the atomic bomb that was used to destroy Hiroshima. So imagine giving every single person on Earth their own small personal nuclear weapon and then detonating those simultaneously. That's something like the destructive force that was unleashed by Chicxulub. It's just, they're unimaginably large numbers. And when this struck, it vaporized a huge amount of rock and target rock and ocean, and and it created a fireball that would have risen hundreds of miles high. And this would have released huge amounts of heat. Just the infrared radiation, the glow from this was visible from, for 1,000 miles away. It was releasing enough heat that anything that saw this would have basically burst into flame immediately. And then after the fireball, there's a vapor plume, which is melted and vaporized material that's shooting up 1,000 miles or more. So this would have been visible across most of North America, much of South America, and probably about as bright as the sun. So the dinosaurs of North America would have seen this thing when it hit for thousands of miles away. And then that's when things start to get really bad. So soon afterwards, there's a high pressure shock wave. Initially, it's traveling at hypersonic velocities. As it moves away, it's traveling at high supersonic velocities. This is traveling outwards, and it's flattening for us. The blast pressure is flattening for us for, 1,000 miles or more away. So these trees are lit on fire, then knocked over, and we have these wildfires that are in over much of North America and South America, perhaps. There are earthquakes that are something like 10 to 11 on the Richter scale. This is an earthquake that is 100 to 1,000 times more powerful than any earthquake recorded in human history. And then the impact is generating tsunamis. It's hitting on the edge of the Yucatan Peninsula on the coast, kind of half in the water, half on the land, and it's creating tsunamis. These tsunamis, again, are unlike anything we know of in history. Close to the blast site, they may have been half a mile high, better part of a kilometer in height. As they swept away, they may have decreased in size, but we're still looking at tsunamis that would have been hundreds of feet tall. These would have inundated the Caribbean islands. They would have swept up through the Western Interior Seaway as far as North Dakota. And these tsunamis would have impacted the coast of Europe and Africa as well. So we're seeing, again, just a series of catastrophes. And now it starts getting really, really bad. So the hot ejecta is shot up into the atmosphere, into the high atmosphere, into space. And as this hot debris is shot up, it then starts to re-enter and rain down. And in some places, as this debris is raining down and it's heating up as it enters the atmosphere, it would have re-radiated that heat. Think of a re-entering spacecraft as it gets red hot. You're basically radiating all that infrared radiation, and this may have started wildfires. This is debated. There may have been some self-shielding effects where basically the debris in the lower layers would have intercepted the heat from the higher layers. Much of the Earth might have been under cloud cover, or if it was raining or something, it would have mitigated this effect potentially. But probably at least over parts of the Earth, I would suspect that just hot debris coming down would have caused fires. This probably was not the main kill mechanism, however. The really dangerous stuff was the debris shot into the atmosphere that stayed up there. This is very fine rock dust. This is pulverized rock, or rock that melts and then recondenses into very small particles. There may have been soot that was shot into space. The target rock was rich in petroleum. So basically this was a giant oil field. As that combusted, it would have created very fine soot that would have intercepted sunlight, and this was shot up into the high atmosphere. And then there would be these sulfate aerosols. These are basically sulfuric acid droplets. It's the same stuff that causes smog and hazes. And this would have darkened the skies. So this would have caused freezing temperatures over much of the Earth, especially at high latitudes. And the darkness would have resulted in, basically, it would have been like twilight at noon. And this would have meant that there was too little light for photosynthesis to be conducted. Plants would not have been able to grow. Algae and photosynthetic plankton in the oceans would not have been able to grow. Photosynthesis stopped, and food production would have stopped. And then basically things started starving to death because there's nothing to eat. Whatever survived the initial days and hours of the impact, all of a sudden, there's no food entering the ecosystem. So this impact winter probably kills something like, again, 90 to 95% of all species on Earth is my guess. That would have included all dinosaurs, with the exception of a handful of birds. But again, most birds were wiped out. Something like maybe 3 to 6 species survived. The plesiosaurs were wiped out, mosasaurs, pterosaurs, ammonites, rudous clams. And also the majority of things that we think of the groups that survived, the majority of their species were wiped out. So that includes mammals, lizards, fish, insects. The majority of these things are wiped out, and something like 80 or 90% of all plant species likely went extinct. So just massive amounts of extinction as a result of this impact winter. Which raises a question. Where does this thing come from? I mean, it's kind of like the metaphorical bolt out of the blue, a lightning strike out of a clear blue sky. It seems to come out of nowhere. There's nothing really like it that's happened to our planet before in the fossil record that we can identify. Nothing like this has happened since. It's just this utterly unique, shocking event. And that's one reason why it took so long for people to accept the idea that this was, in fact, the driver of the dinosaur extinction. So where the heck does this thing come from? And various ideas have been put forward of the origin and type of the extraterrestrial impactor. The simplest and most straightforward hypothesis is that it's an asteroid. This makes sense. There's a lot of asteroids in the asteroid belt, after all. They occasionally wander into orbits near Earth. These are the near-Earth asteroids and the Earth-crossing asteroids that cross our orbit. And that's one potential source, and the obvious one. And the abundance of iridium in the debris field and the layer, the fallout layer, the KPG boundary clay, is consistent with this. Statistically, it seems like the most likely and obvious explanation. The issue is, of course, in science, the most likely and obvious explanation isn't always the right one, or we wouldn't have to do so much science if it was easy like that. If a hypothesis has a 90% chance of being right, then 10% of the time it will be wrong. So you can say, 90% of the time that this happens. So, well, sometimes it doesn't. So we should, of course, start with the obvious, start with the simplest explanation that fits the facts, but then double check all the possibilities. So yeah, probably an asteroid, but let's look at some other possibilities out there. A minority view held that the Chicxulub impactor could represent a comet. This is statistically less likely. Comets like Halley's Comet are big events when they happen because they're pretty rare. We don't see a lot of comets flying around the solar system. And comets are mostly ice, so it's unclear whether a comet would have enough iridium to produce the iridium signal that we see in the Cretaceous-Paleogene boundary clay. Another possibility might be an interstellar object. In recent years, we've discovered a number of interstellar objects. These are like Oumuamua, Borisov, and Atlas. These are bodies traveling at very high speeds through our solar system, and their speeds exceed the escape velocity of the sun. What's that mean? That means they can't be in orbit around the sun. They're traveling too fast. So they're not part of our solar system because they're not in orbit. They're coming from somewhere else. They're coming from outside of our solar system, from another star system entirely. And we've only started looking recently for extraterrestrial, for interstellar objects, but we've already found several of them, which suggests they're maybe a lot more common than we think. And as we get better at detecting them, we'll see more of these things. As far as I know, no one has ever proposed that Chicxulub was caused by an interstellar object. So I'm going to propose that theory now. Chicxulub was from another star system. Now, do I think this hypothesis is likely? No. But now, every single time someone reviews this topic, they'll have to cite me to dismiss it. A fringe hypothesis proposed by Longridge that no one serious actually believes is that Chicxulub is an extraterrestrial object. Well, okay, but I mean, to be serious about it, Chicxulub is a really weird event. And again, in science, we want to go with the simplest hypothesis that fits the facts, but Chicxulub is so completely outside of our normal experience as biologists, as paleontologists, as geologists, as astronomers. We should at least be open to the idea that something really weird happened here. So, maybe not an interstellar object, but, it's a pretty unusual event. We should probably kind of look at all the different possibilities. So we do have some more evidence on this over the years. Additional evidence has come to light, which is helping us constrain this a bit. And it seems to suggest that it is, in fact, an asteroid. And furthermore, it gives us some idea on what type of asteroid this was. So in 1998, a paper was published on this tiny little fragment of rock that was recovered from a Cretaceous-Paleogene boundary section that was extracted from the middle of the Pacific Ocean in a deep-sea drill core. And so it dates to the time of the impact. It's kind of in the middle of the iridium anomaly, and it was identified as a piece of asteroid, confirming the asteroid identification, and furthermore, the composition suggested the KPG asteroid, the Chicxulub asteroid, was part of a class of asteroid known as carbonaceous chondrites, so named because they're rich in carbon. Now, it turns out that different asteroids have different chemical signatures, abundance of elements like iridium, but also different isotopes of various other metals, and isotopes being heavier and lighter forms of certain elements, a chemical fingerprint, if you like. And if you can match up the isotopic ratios of different elements, that might tell you something about what class of asteroid this comes from. And close study of the Cretaceous-Paleogene boundary sections, the metals in there, shows an elemental fingerprint, isotopes of a thing called ruthenium that are consistent with carbonaceous chondrites. So it confirms what this little fragment was telling us, that the Chicxulub impactor was, in fact, a carbonaceous chondrite. In some ways, it's not surprising. It kind of told us what that little fragment did. What is surprising, having this confirmed, is that none of the other big impacts we know of are caused by carbonaceous chondrites. They're typically of ordinary, non-carbonaceous, not particularly carbon-rich chondrites. And so this is kind of interesting. So, okay, it turns out my pet theory that Chicxulub comes from beyond our solar system is nonsense. It has an elemental signature consistent with emerging from inside the solar system. But I was right about one thing. Chicxulub is really weird. It's coming from a different part of the solar system than most of the other asteroids. It's this carbonaceous chondrite, which is forming fairly far out. These things would form out near or beyond the orbit of Jupiter. So it is unusual compared to these other impact events, which are mostly not carbonaceous chondrites. So what's so special about them? Well, carbonaceous chondrites are, as the name implies, rich in carbon compounds and organic molecules, because carbon compounds are the stuff that make up life. These would include amino acids, nucleic acids. They have a lot of really complex compounds inside them. And these can form something like anything from 1 to 3% of the mass of a carbonaceous chondrite can be these organic compounds. Another unusual thing about carbonaceous chondrites is they are incredibly rich in water. By weight, they can be anything from 5 to 20% water, to be more specific, typically in the form of ice. But this is unusual. Your stony asteroids do not have lots and lots of carbon and carbon compounds. They don't have lots and lots of water in them either. So these things are incredibly old. Carbonaceous chondrites are some of the oldest things in the solar system. You can buy these things online. You can buy little fragments of them, and you can hold in your hand the oldest thing that you can possibly hold in your hand. These goes back, to the dawn of the solar system. Literally, these chondrites are forming at the same time the planets are forming. They actually form slightly before the Earth and slightly before the Moon are forming. And so radiometric dating of these things has helped, getting the age on these chondrites has helped constrain the origin and evolution of Earth and the solar system. And the little individual grains inside of them, these things called chondrites, date to something like 4.56 billion years old. So again, to touch one of these things is to touch the oldest thing you can possibly touch, the oldest thing in the world. They are leftover fragments of creation. They are fossils of the early evolution of the solar system. And as these sort of fossils, they actually show the process by which the planets formed, by which the solar system evolved. We see in these things, you chop them open, you see the process of accretion. So how do the planets form? Well, we have this disk of hot debris forming around the early sun, and as it cools, this hot debris starts condensing into grains of minerals. And so you have these things, maybe a millimeter to a few millimeters in size, these like pebbles and grains of minerals. And these things start clumping together. They start hitting each other and clumping. Gravity starts pulling them together, and the little tiny grains clump into larger rocks, which clump into bigger rocks. They form cobble-sized structures, and then boulder-sized structures, and then great big rocks. And they start condensing. The big rocks clump into bigger rocks, and so on and so forth, forming protoplanets called planetesimals. And these planetesimals, these protoplanets, then collide with each other, forming planets like Earth. So we are seeing here in cross-section, the process that formed the solar system, that formed the Earth, that formed the planets, we are seeing a fossil of planetary evolution. What's interesting here is that different asteroids that form at different parts of the solar system are preserving different parts of that evolution, and different things are happening in different parts of the solar system because there's different elements in different areas, different minerals, and different temperatures. So these things are forming fairly far out, well beyond Earth's orbit, beyond Mars' orbit, close to the orbit of Jupiter or beyond that. This is where the carbonaceous chondrites form. So they form in a very different way than the planetesimals that form the Earth and the Moon. So what's the implication of that? The carbonaceous chondrites, being rich in water and organics, couldn't form in the inner solar system. It was just too hot there. Volatile compounds like water would boil off out of the early solar system, and then they would freeze in the outer solar system. They would turn to ice where it was cold. And this is out beyond the orbit of Mars. This is out past a zone they call the snow line. So beyond the snow line, water and other volatiles could cool enough to where they could condense. And then this really extraordinary chemical alchemy starts to happen. So once we have these minerals and ice kind of condensing there and they form planetesimals, radioactive elements that are inside these planetesimals start to heat up their cores a little bit and melt that water. And then the water starts reacting with the minerals and the carbon compounds, and it produces all these crazy, amazing organic compounds. It's like this great big chemistry experiment that's happening out past the snow line, and it starts making really, really complex organic molecules. So inside of these carbonaceous chondrites, we start finding, you crack these things open, and there are all these organic compounds. These are complex molecules using carbon as the backbone of these molecules. And these include a lot of the building blocks of life. We are seeing amino acids, which can be chained together to make proteins. We're seeing nucleic acid bases that can be chained together to make DNA and RNA. We're seeing fatty acids and sugars. We're seeing hydrocarbons and all types of crazy molecules. Now, on Earth today, you don't get these sort of complex organic molecules forming. Amino acids and nucleic acid bases don't form naturally. They're only made by living things, which creates this kind of chicken and egg problem. Okay, so if living things are formed out of amino acids and nucleic acid bases, how can living things be formed out of these things if there weren't living things to make them in the first place? And carbonaceous chondrites show us that these things were being formed naturally out past the snow line. And that's part of the answer of how life evolved. At least the raw material of life, a lot of it is delivered to Earth by these carbonaceous chondrites. And then this forms kind of the raw building blocks that can be combined to start creating things like proteins and DNA and RNA and life. Carbonaceous chondrites are the stuff of life. So soon after Earth is formed, it's dry. Because again, in the inner solar system, you don't get a lot of water in there. So there are no oceans or seas or lakes or rivers. So life couldn't evolve. But then there's a rain of chondrites coming from the outer solar system that's thought to have brought water to the Earth. And it's bringing enough water to bury it to an average of today 2 miles, which tells you something about how many chondrites had to fall to Earth, if they're about 5 to 20% water. So these chondrites are coming in, they're delivering the water, and that's creating the oceans and the rivers and the lakes and the seas. But if there was enough water coming in from these things to create oceans, they must have been delivering vast quantities of carbon compounds as well. And these would have become some of the raw materials for life. So in volume, we could imagine that these carbon-based compounds would have been something like, given the ratio of carbon to water in these asteroids, they might have delivered something like 15 to 20% of the volume of the oceans of these carbon-based molecules. Amino acids, nucleic acid bases, and fatty acids and all this stuff. So imagine the early Earth, not with this pristine blue seas, but organic slicks and sludges and crusts and goos and foams and films, an early Earth awash in organic compounds, this vast chemistry experiment, and these chemical compounds then start undergoing reactions to give rise to life, to living things, to bacteria, to archaeans, to eukaryotes, to dinosaurs, and to humans. Carbonaceous chondrites are the stuff of life. We're chondrites. Maybe most of the stuff in our bodies, and the bodies of all living things, bacteria and dinosaurs, trilobites and pterodactyls. A lot of this stuff, the water and the carbon that makes up our complex organic compounds, appears to have been delivered by Earth by these carbonaceous chondrites. So these things gave rise to life, which is a deep irony, because 4.5 billion years ago, a chondrite, the Chicxulub impactor, will become an engine of destruction. So again, the carbonaceous chondrites like the Chicxulub impactor are thought to form in the outer solar system out past the orbit of Jupiter. But most of the carbonaceous chondrites we know of that we've observed are in the main belt of the asteroid belt. So that's probably where the Chicxulub asteroid is coming from. So how does it get there? How does it go from out past Jupiter into the asteroid belt? So this is kind of this long, strange odyssey. Models now suggest that Jupiter hasn't always been where it is, that it's wandered over time. And soon after Jupiter forms, it starts to wander inwards towards Mars, and as it does, it shifts a lot of these chondrites out of their previous orbits, and some of them are knocked out of the solar system entirely, some spiral into the sun, some are knocked into planets, but then a lot of these things end up parked in the asteroid belt. And once they're shifted out of their previous orbits by Jupiter into the asteroid belt, they just kind of circle there for billions and billions and billions of years. Which then raises another question. Why didn't Chicxulub stay in the asteroid belt with all the asteroids? And again, that has something to do with Jupiter. So it's likely that the Chicxulub asteroid got caught up in a gravitational interaction with Jupiter. This is sort of orbital dance, whereas we have these things, asteroids circling and Jupiter circling. If the timing of the orbit comes into sync, the gravitational poles will start to interact repeatedly. So if, for example, an asteroid orbits the sun twice for every time that Jupiter orbits the sun, it's got a 2-to-1 resonance. We could have a 3-to-1 resonance, where 3 asteroid orbits for every single orbit that Jupiter makes. There are 5-to-2 resonances and 7-to-3 resonances. And so they're kind of in tune with each other, doing this dance. The repeated passing of Jupiter will kind of tug on it a little every single time. It's give a nudge, 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 until eventually it knocks this thing out of orbit. And these asteroids are shot out of their orbits. And again, they can fly out of the solar system, they can fly into the sun, or they can fly into another planet. And we can see this in the distribution of the asteroids. There are these gaps in the orbits. The asteroids are basically in the asteroid belt where basically nothing's there in these gaps. Because if you get into that gap, you're in resonance with Jupiter, and it tends to knock you out. So as long as you stay out of these gaps, out of these zones where you get into resonance with Jupiter, you're fine. You can circle forever. So what happened to the Chicxulub asteroid impact that for some reason it left this safe zone and wandered into one of these dangerous zones where it got into resonance? And this is likely something called the Yarkovsky effect. This is a crazy thing. It creates a sort of natural thruster or photon drive for the asteroid, almost turning the asteroid into a kind of spacecraft, but a really, really, really slow one. So photons actually transfer momentum, little photons that light is made up of, and they can be used for thrust. There's the concept of a solar sail, for example. You get a great big reflective sheet, you shine sunlight on it, and it can slowly accelerate a spacecraft over. It takes a while, but you can just use sunlight to accelerate things. And asteroids can do something sort of similar, but a bit distinct from a solar sail. What happens is as the asteroid is rotating, the sunlit side absorbs the photons and turns them into heat. And then it starts turning, and it starts re-radiating those photons off as infrared, in the infrared spectrum, going from visible into infrared, and it redirects that thrust off at an angle. And so basically the emission of photons, the heat that's radiated away as the asteroid starts turning, radiates it off in a different direction. It creates thrust. And this is really, really weak. But it can decelerate the asteroid into a lower orbit. It can accelerate it into a higher orbit. Again, very, very gradually over millions or billions of years. But it can change the orbit's of the asteroids until they get into resonance and they're shot out of the asteroid belt. So we have a lot of asteroids that we can observe where this has happened to them. These are the near-Earth asteroids, and they're thought to result from this combination of the Yarkovsky effect and this orbital resonance, where Jupiter has thrown them out of their asteroid belt after they kind of wandered into a dangerous orbit. And there are tens, maybe hundreds of thousands of them. We've found almost all the big ones, we think, but we haven't even found 10% of the ones below 100 meters. So there's huge numbers of these things out there, but relatively few large ones, curiously. There are only around 1,000 of these things that are larger than 1 kilometer in diameter, and we think we found almost all of these guys. So again, not a heck of a lot of big ones out there, and few really big ones. So in terms of Chicxulub-sized impactors, that is, 10 kilometers or 6 miles in diameter, there are only a couple that we know of. There's the asteroid Eros, which is about 10 miles across, and one called Ganymede, which is about 22 miles across. So how often does this happen? Well, asteroids in the inner solar system aren't there forever. These things haven't been out there for billions and billions of years. Once they get into the inner solar system, their orbits are kind of unstable and they tend to fly off somewhere, get lost, or crash into something. So they're constantly ejected into this inner solar system and then lost. And the residence period might be a few million years for the smaller ones, possibly a few tens of millions of years for the longer ones. So assuming the big ones are out there for something like 20 million years, and we currently have 2 big ones out there, then over the course of the past 2 billion years, maybe around 200 Chicxulub-sized bodies have wandered into the inner solar system. So that gives us an idea of, in terms of potential large asteroids that could cross Earth's orbit and hit the Earth, probably a few hundred of these things over the past couple billion years, of which, we know of one, Chicxulub, that's actually hit. So again, it seems, something on the order of 1% or a couple percent of these things that wander into the inner solar system actually hit us. And that number, however, there might be a few more things that have hit us than we recognize for a couple of reasons. So one problem is, when you study impact geology, is that our record of impacts is almost entirely terrestrial. We only find craters on land. Now, partly it's just hard to look in the ocean. The deep ocean is hard to study. That's part of the reason. Not a lot of geologists at the bottom of the sea, obviously. Another issue is that, when an asteroid hits the ocean, unless it's pretty big, it's not going to penetrate the seafloor. It's not going to leave a trace there. It might have to be as big as, a kilometer or more to get down into the deep ocean and hit the bottom of the ocean and leave an actual crater. At very high speeds, impacting water at high speeds, the water doesn't flow away. It acts like a solid, basically. That's why jumping off of a tall bridge is so dangerous. So basically, if you think of the water as almost acting like an upper layer of rock, it has to punch through that water to leave a trace, and only very big ones can actually do that. So we don't see a lot of craters in the sea floor. Another problem is that the ocean floor is really young. Ocean floor is constantly being recycled. At the mid-ocean ridges, volcanoes erupt, they create new rock, and then it's subducted at these trench zones. So the average age of the ocean floor is only about 100 million years. The average ocean floor rock is younger than Brontosaurus at 150 million years. We have almost nothing from 200 million years ago or older. So almost all of the older craters on the ocean floor have been destroyed by recycling of the ocean floor. So that's another reason we don't see big craters in the ocean floor. So between these things, it's hard to explore the ocean floor. Only big impacts would leave craters. The older craters are destroyed. We are basically missing all these ocean impacts. So we only have records of asteroid impacts from, say, 29% of the Earth that's actually land. So we need to kind of divide our figures for impact frequency by 0.29 to account for this. So if we have one great big Chicxulub style impact on land, then maybe there's a total of 3.4 on average big impacts, the couple in the ocean that we're missing. So one impact on land, a couple in the ocean we're missing. So, this gives us a frequency, assuming a couple hundred bodies have flown into the early solar system in the past couple billion years, then a hit rate of something like 2 or 3% maybe. So, not, I mean, only, actually, it's about, I don't know, about 2% roughly of those impactors actually hit the Earth. We may also be missing some craters due to erosion. That would kind of up the frequency of impacts. But still, we're looking at a very, very low rate of large impacts into the Earth over the course of the past 2 billion years. So these are not meant to be exact figures, but just to explain that a lot of asteroids probably did the exact same thing that Chicxulub did and were knocked out of their orbit in the asteroid belt. They came into the inner solar system, and then basically they missed. So the hit rate of these things thrown in at us is probably on the order of 1 or 2% or maybe less, assuming there's a lot of, just depending on the flux of these things. So it's kind of like a game of Russian roulette, sort of cosmic Russian roulette. So in a game of Russian roulette, you've got a revolver, a 6-shot revolver, and you have the cylinder with 6 chambers, and you put 1 bullet in that cylinder. You spin the cylinder and you pull the trigger, and the odds are in your favor, actually. You have about 1 chance in 6 of the gun going off and killing you. But obviously the consequences of losing are pretty high. So you're probably going to win, but if you lose, you're going to lose big. It's a low probability, high impact event, both literally and metaphorically. It's pretty high impact. Imagine a game that's a bit like Russian roulette, but instead we're playing over billions of years. Instead of bullets, we have asteroids with 100 billion megaton impact yields, and our gun has 100 chambers, and only 1 is loaded. And we keep pulling that trigger once every 20 million years, roughly. And nothing happens, and nothing happens, and nothing happens, and nothing happens, and eventually something really, really bad happens. That's kind of what's happening here. Basically, we're playing Russian roulette with the solar system until eventually our luck runs out and something really, really bad happens. So seen in this light, something like the Chicxulub impact, while it might be infrequent, it would be inevitable. Earth's luck just ran out. For billions of years, we were dodging bullets, or rather asteroids. Things are thrown into the early solar system. They circle for millions of years. Most of them just spiral into the sun. They're thrown out of orbit. Maybe a few hit Mars or Venus and the moon, and eventually 1 hits us. So seen in this light, the extinction of the dinosaurs, the impact of the Chicxulub asteroid, wasn't a fluke, but the inevitable outcome over a long enough period of time, a highly improbable event, once in a billion years event, becomes probable. So raises some interesting questions. Is it likely to happen again? Statistically, it's inevitable. We should expect, maybe 100-kilometer crater to be formed every 100 million years or so, and smaller ones more frequently and bigger ones more infrequently. So eventually this will happen, but we'll probably have to wait millions of years for something to even get a crater that's 60 miles in diameter, and might have to wait hundreds of millions or billions of years to get a crater as big as Chicxulub. But it will happen eventually, but we probably won't be here, and probably human beings won't be either. But it raises an interesting question. So we have asteroids hitting. Big ones like Chicxulub are very rare. Smaller ones are more frequent. We've had a number of different craters that have occurred. Why don't we see any of these other craters causing extinction events, however? Even if they're smaller than Chicxulub, wouldn't you expect a smaller extinction event from something like the Chesapeake Bay crater? Even if it's not quite Chicxulub level, maybe at least a few mammals would get wiped out or something like that. So this kind of raises some interesting questions. Is it just the fact that you need to get up this really, really high threshold? You need to have a 6-mile diameter asteroid before you can hit the threshold of not launching enough debris into the atmosphere to cause an extinction? Or is something else going on? Is there some reason why this event was so destructive and all these other asteroid impacts over time have not been? One possibility is that Chicxulub might have hit the Earth in an unusually vulnerable spot. The target rock that was struck by Chicxulub may have magnified the damage done by the asteroid impact. So one issue is that a hit in the ocean creates a lot of steam. And whereas a hit on land creates a lot of rock dust, which kind of just falls back down, but the steam creates this vast vapor plume that helps shoot debris into the high atmosphere, and it might help load the atmosphere with debris in a way that a continental one wouldn't. Meanwhile, a hit in the deep ocean would just not liberate a lot of rock, mostly liberate a lot of water, and that just comes down as rain. So maybe it's that combination of hitting right on the edge of the ocean, launching a lot of rock mixed in with a lot of water might have made this more dangerous. And it's also the case, however, that the composition of the target rocks might have been unusual in addition to the site of the impact on the edge of the ocean. So how was Chicxulub found? The crater was originally, the structure was discovered but not recognized in the 1970s because Pemex, the Mexican oil company, was looking for oil. And everywhere around that area is rich in oil. So it's the middle of an oil field. And when it came in and it hits, it's barreling in at 50,000 miles an hour, it's going to instantly, vaporize all that oil, shoot it up into the atmosphere, and it's going to burn and create soot. If it hit somewhere else, it wouldn't have done that. So the soot added to the ejecta may have made the impact more dangerous. Another issue with the target rocks is they're full of gypsum. And gypsum is a mineral that's rich in sulfur. It's a sulfate mineral. And when this target rock, this gypsum is blasted and shattered and vaporized and cooked, it releases these sulfates. It creates sulfur dioxide. This then mixes with the water, the boiled ocean that's being shot up into space, and this creates sulfuric acid that creates these droplets. So we have these fine sulfate droplets that are shot into high atmosphere. It creates a sulfate haze similar to like a smog, human-created smog or volcanic smog. And this intercepts sunlight and helps block out the sun. And this stuff may have stayed up there for years. So this combination of features, hitting on the edge of the ocean, mixing rock with a lot of water and steam, hitting sulfate and creating sulfuric acid droplets, hitting petroleum, burning it and creating soot, this may have created a uniquely dangerous impact that would a dirty impact that launched a lot of crap into the atmosphere and helped create this really severe impact winter. And on top of that, there's also the issue of the angle of impact. It may have been the way it came in. If it coming straight down, more stuff might have gone straight up and then straight back down. But by hitting at an angle, about a 60-degree angle from the horizontal, it's spraying all this stuff into the atmosphere and may have increased the loading of debris into the atmosphere. So it may have hit at just the wrong spot at just the wrong angle. So the asteroid seems to get really lucky or very, very unlucky if you're a dinosaur. So in the original Star Wars, hopefully this isn't going to be a spoiler for you guys, to blow up the Death Star, this giant super weapon of the Empire, there's this one little spot. You need to precisely hit this spot, this one little vulnerability, this thermal exhaust port, which is 2 meters in diameter. You got to precisely hit it with your proton torpedoes. And if you do, the entire thing blows up. You could kind of argue that this is sort of cliched, lazy writing. It's kind of a plot device that gives the lone hero the chance to magically save the day and do his heroic hero stuff. But this is kind of what's going on with Chicxulub, you could say. It's like the Earth has a thermal exhaust port, which is target rock on the edge of the ocean, which is rich in petroleum and sulfate. And if you hit it there precisely, it creates a mass extinction. And if you hit it somewhere else where you didn't have this petroleum, where you didn't have the sulfate, where you didn't have the kind of the edge of the ocean, or you're on the continents or in the deep ocean, maybe you wouldn't have a mass extinction, which is really extraordinary to think about. So this is the fatal flaw. It's a time-honored trope in mythology and storytelling. And, all sorts of characters have this weak spot. Smaug the dragon in The Hobbit has only one spot on his body where he's not armored. And Bard the archer hits him there with an arrow and kills him. Achilles has his Achilles heel. It's the only place he's vulnerable, and he's struck in his Achilles heel and he dies. Voldemort has his Horcrux from Russian fairy tales. Koschei the Deathless has his death kept on the head of a pin. And the pin is inside an egg, which is inside a duck, which is inside of a rabbit, which is inside of an iron chest. And the iron chest is buried under an old oak tree on the faraway island of Bouillon. Did Earth have a fatal flaw? Did it have a weak spot? And you have to hit it just the right point, and evolution goes off in this totally different direction. And it may be that something like this, that may be that like there are a handful of places on the entire planet, maybe something between 10 or 15% of impact sites on Earth would have been this devastating, maybe even fewer, maybe one or two places on the Earth would have done this much damage. But yeah, Earth has this fatal flaw, weak spot, you hit it, dinosaurs go extinct, mammals start evolving. This might kind of seem like cliched writing. Maybe that's a hint we're in a simulation. The writers are being lazy. Yeah, how do we make this transition go from dinosaurs to humans? I know, we'll have a magic weak spot, and you just hit it with the asteroid, and boom, dinosaurs are gone, mammals take over. Perfect. You remember what I was saying about this event being really, really weird? I'm not saying God exists, but I'm saying if he doesn't, believe whatever you want, man. It's a free country. But if this is true, it kind of makes you go, whoa. So, conclusions. The more I dive into evolution, the big scale stuff, macroevolution, evolution over billions of years, millions of years, the less I really know about anything. The world is a pretty amazing, mysterious place, and it's a very improbable place. And the more I learn about evolution, the less it really makes sense to me. The more remarkable, implausible, almost magical it seems. I'm not saying we're in a simulation. I'm not saying God did it all as an answer. But to be fair, when the creationists say that our evolutionary theories require a lot of strange, incredibly unlikely things to happen, a lot of coincidences, almost miracles if you like, they kind of have a point. I'm not saying the world is 6,000 years old, but I'm saying it's a really weird, mysterious place, which is interesting to think about. Over long periods of time, incredible events, disasters, catastrophes, near miracles happen. And these are often the same event. A catastrophe for dinosaurs was a miracle for the mammals. Darwin emphasized the role of everyday processes in evolution. What he failed to appreciate is that over million-year or billion-year timescales, fantastically improbable things happen. We're unlucky, for example, to win the lottery, to get struck by lightning, or to be attacked by a shark. These are these are not everyday things. They are not likely to happen as you walk down the street. If you could, however, live for 100 million years, you would win the lottery many times, get struck by lightning many times, and be attacked by a shark many times. It would be almost inevitable that these highly improbable events would become probable over long periods of time. And so when we look over the course of evolution, over tens of millions of years, hundreds of millions of years, billions of years, really weird, crazy stuff is going to happen, like the Chicxulub impact. But the Chicxulub impact is not remarkable just in its size. That alone makes it kind of a 1 in 100 million year or 1 in a billion year event. But it's improbable, and it seems to happen in just the right way or just the wrong way if you're a dinosaur to wipe out the dinosaurs. It hits this target rock that's rich in sulfates, and it's rich in oil. It hits on the edge of the ocean, liberating all this steam that can then react to the sulfates and launch everything into the high atmosphere. It's hitting at just the right angle to do the most possible damage. As disasters go, it's almost perfect, maybe too perfect. It's the sort of perfect storm or perfect impact where everything comes together in just the right way, in just the wrong way, in such a way that makes you start wondering about God and fate. I mean, statistically, how likely is this? I mean, over time, we're going to see events that happen every 100 million years or once every billion years. I mean, over the course of Earth's history, we should see a once in a 1 billion year event about 4 or 5 times, given that we're around for 4.5 billion years. But this might be an event that is far, far more improbable than that. When you say, okay, we've got this once in a billion year event, something on the order of the Chicxulub impact, and it happens to hit in the exact wrong place at the exact wrong angle to create this extinction, you might be looking at something that's like a once in a 100 billion year event or a once in a trillion year event. It might be that improbable. So not just the size of the impact, but the nature of the impact adds to its extraordinary improbability. It hit in the exact right place to wipe out the dinosaurs and give mammals and humans a chance to evolve. And the extinction was severe enough to wipe out the dinosaurs, but it's also kind of lucky that it wasn't. If it had been any bigger, it might have wiped out all the mammals, and we'd be all the way back at frogs and lizards, and maybe we wouldn't have evolved intelligence. So you could kind of argue it's the sort of Goldilocks level of catastrophe. It's severe enough to shake things up and wipe out the dominant animals in the form of dinosaurs. It's not so severe that it wiped out mammals entirely. It's just right. And again, what are the odds that everything would go wrong in exactly the right way for us to be here? And again, this, you start thinking like maybe this is a once in 100 billion or once in a trillion year event. What are the odds of that happening? Well, the thing is, the odds of that happening on Earth might be low, given that we've only been here for a few billion years. But evolutionary history doesn't just span a long time. It encompasses a vast universe, of which we are just one planet. There are hundreds of billions of stars with trillions of planets in our universe. There are trillions of galaxies in the visible universe. So if it takes a rare set of circumstances for humans to evolve, a once in a 100 trillion year event, that's likely to happen somewhere in these billions and trillions of planets. This extraordinarily unlikely event, it's going to happen somewhere, not many places. And maybe, just maybe, we're that rare world where the planets just literally came into alignment and everything happened in exactly the way it had to for us to be here. So maybe we're incredibly lucky, or maybe someone has a plan, whether it's God or whoever's behind the simulation. I don't know. It makes me think, though. Arthur C. Clarke once said that any sufficiently advanced technology was indistinguishable from magic. To paraphrase him, I would suggest that any sufficiently improbable evolutionary event is indistinguishable from magic. This impact, there is something extraordinary, remarkable, almost magical about this event that led to our evolution and our existence.